Welcome to the Explainer. Today, we're jumping right into part one of our series on system protection, switchgear, and instrument transformers. Specifically, we're looking at dependability, security, and CT/VT accuracy. If you've ever wondered how the grid decides when to instantly shut down a line versus when to keep the power flowing, it all comes down to a fundamental engineering tension and, honestly, the absolute physical limits of the sensors monitoring the system. Let's get right into it. Protection engineers live constantly between two extreme, completely opposite failure modes. Picture this. On one hand, a relay fails to trip during a real fault. What happens? Equipment burns, breakers spark, and catastrophic damage just spreads across the substation. On the other hand, you've got the exact opposite nightmare. A relay trips falsely during normal operation. It essentially detects a phantom issue and needlessly blacks out a perfectly healthy section of the grid, leaving customers who did nothing wrong in the dark. Every single protection design decision on the grid is a massive trade-off between these two risks. ESCOM actually sums up this high-stakes reality perfectly. They note that for the substation to perform, it needs sophisticated protection equipment to detect faults. And this action is absolutely necessary to protect people when there's an accident or to keep the electricity supply constant when things are fine. You have to navigate this compromise flawlessly. It's not just about saving metal and wire, it's about keeping the lights on and the public safe. So let's put some formal names to these two sides. First up, dependability. This is the absolute certainty a relay will operate correctly and trip the breaker for every actual fault within its designated zone. When you prioritize dependability, you're basically saying, I absolutely cannot afford to miss a fault. Missing one is a dependability failure, leading to ruined infrastructure and severe safety hazards. And on the flip side, we have security. This is the absolute certainty that a protective relay will not operate falsely for normal operations or for faults that occur completely outside its designated zone. Prioritizing security means you're saying, I cannot afford a false alarm. Now, a security failure might not mean broken equipment, but it does mean angry customers sitting in the dark for absolutely no reason, creating unnecessary disruptions to the larger network. The crucial takeaway here is that you genuinely cannot maximize both simultaneously. It's like a dial. If you crank that dial all the way to maximum dependability, your system gets so sensitive it'll trip at the slightest voltage dip. There goes your security. Turn it to maximum security, the system becomes so stubborn it might ignore a real fault. Every relay setting and every scheme design is a deliberate trade-off tuned to what's more costly in that specific application. But here's the catch. To make that delicate dependability versus security decision, the relay needs perfect data. So how do relays actually see the grid to make these choices? I mean, they don't interact with the massive 500 kilovolt high voltage lines directly. If they did, they'd instantly vaporize. They have to rely on translators. We call these translators instrument transformers, and may act as the eyes of the entire protection system. You've got current transformers, or CTs, which step down the massive primary currents flowing through the lines, and voltage transformers, VTs, stepping down the extreme high voltages. They deliver safe secondary signals, usually around 1 amp or 5 amps, right to the relays. But remember this, the relay's logic is only ever as good as the signal it gets from these transformers. Which brings us to a major complication: heavy fault currents and DC offset. What happens when the grid is under extreme stress? Well, during a power system transient, like a massive short circuit, the fault current is not some nice, clean, symmetrical wave. It gets messy, highly asymmetrical. Take a look at this decaying DC component. It literally pushes the entire current waveform off its center axis, creating a massive instantaneous fault current. And the severity of this really depends on the circuit's X/R ratio. A highly inductive system means that the DC offset decays very slowly, and that puts immense physical stress on the sensors trying to read it. And here is exactly why that physics lesson matters for our relays. CT saturation. When that massive DC offset heavy fault current hits the current transformer, it can completely overwhelm the CT's internal iron core. The core physically can't contain any more magnetic flux, so it saturates. The output waveform sent to the relay distorts and flattens out, so your relay ends up getting false, understated current readings exactly when it needs absolute accuracy the most. This leads to a really critical engineering distinction. You have to use the right equipment. Protection class instrument transformers are specifically designed with larger cores to handle these high current, high distortion conditions without saturating. Metering class transformers, on the other hand, are highly accurate for normal daily power flows, but they saturate so easily during a fault. Seriously, using a metering class CT for protection duty is a massive career-limiting design mistake. It'll saturate, the relay will underread the fault, and it just won't trip. And we shouldn't forget about voltage transformers either. VTs have parallel problems. The excitation current drawn by the VT's own magnetic core introduces these small ratio and phase errors between the actual system voltage and what the relay measures. This is exactly why strict accuracy classes exist for both CTs and VTs. You have to ensure the relay gets a mathematically dependable picture of the grid's health. Okay, let's do a quick knowledge check to lock this all in. Imagine you're reviewing a fault report. A relay underreads a severe, close-in fault with a high DC offset, causing a dangerously delayed trip. What is the likely cause of the sensor failure? If you said CT saturation, you hit the nail on the head. That heavy DC offset drove the iron core of the current transformer right into saturation, the waveform flattened out, and the true severity of the fault was essentially masked from the relay, forcing that delayed trip. This is exactly why the dependability versus security trade-off is so tough. Your sensors can absolutely lie to you under extreme stress. But, modern grid engineering isn't just standing still. We're actively moving past the physical limitations of traditional iron core instrument transformers. The evolution taking place right now involves solving this saturation issue completely by transitioning to digital process buses. The real game changer here is the IEC 61850 process bus architecture. Step 1, you replace those heavy iron core CTs with next-gen optical CTs that literally use light to measure current. No iron core means zero saturation. Step 2, devices called merging units, or MUs, sit out in the yard and digitize these base quantities right at the source. And step 3, that synchronized digital data is published directly to the relays over a high-speed Ethernet process bus. The advantage of these merging units is pretty staggering. Instead of analog wires carrying dangerous voltages into the control house, the MU publishes universal datasets: voltage, current, breaker status, the whole shebang. For standard protection, the base sampling rate is an incredible 80 samples per power system cycle. For high-frequency applications, like power quality, it's hitting 256 samples per cycle. The relays simply subscribe to this clean, perfectly aligned digital data, getting a flawless, saturation-free picture of the fault. So, wrapping this up, you might have started this explainer thinking protection is just detect a fault, trip a breaker. But in reality, it's that dependability versus security trade-off shaping every single setting decision. And more importantly, the physical accuracy limits of your CTs and VTs dictate what the relay actually sees. You simply cannot protect what you cannot accurately measure. Which leaves us with a fascinating final thought for today. Now that you know the absolute limits of the sensors, the threat of CT saturation, and the high-stakes trade-off between dependability and security, how do engineers actually take this raw data and structure the overcurrent, distance, and differential relay schemes to size the breakers and protect the grid? Think about how you design a logic scheme that never falsely trips, but never misses a fault. We're going to unpack exactly how the industry solves that massive puzzle in part 2. See you then.